titrations you should know already. You should know that this is called a burette, right? You should know that I pipetted exactly 10 mils so that it was a more exact measurement of my volume. So it's 10.00, whereas if I used a measuring cylinder, it could be 10.1 quite easily. It's not as exact, precise measurement. So burette and a pipette to get my volume in there. Okay. Then we have an indicator, right? And you did these titrations in Chem 20. You will have taken an average volume until you got, or you would have reduced the volume until you got an endpoint change, right? And so we have a known concentration. We will have a known volume. You have a known volume, and you're solving for that concentration. That's what we did in Chem 20. And you had to do it 3 times because you're not so precise with this endpoint pink, light pink, dark pink. So therefore you do it a few times until you take the average and get a nice calculation. Everybody remember this? Chem 30 is about the what's exactly happening here. Okay? So in here I have my sodium hydroxide. In here I have my hydrochloric acid. If I were to stick this pH meter, so this is a pH meter, turn it on, they never ever work. You always have to calibrate them. They take forever to calibrate. I don't like using them. But it's like a digital thermometer. You stick it in and it gives you a number, and the number is your pH. Okay? If this were to work, and I were to stick this into my acid, my HCl acid, what pH would it be?
Lower than 7.
Less than 7. Can you be more specific?
1 to 4.
Why 2? Why 2?
Because it's a strong.
It's a strong acid.
I don't even know why it's less than 7.
Because it's an acid. Okay, so it's a strong acid. And in fact, I'm not even going to say 2, although you might have said 2 because in biology, this is stomach acid, and they say stomach acid is pH of 2. Okay? But that's rounding, it's 1 point something. So we're going to call that 1. Strong acids, pH 1. This is NaOH. What's pH is it going to be if I could stick the thing into here? NaOH. Strong base, so 14. Everybody with me? Okay. So I have HCl in my flask down here, and you're saying it has a pH of 1. And NaOH up here, and you're saying it has a pH of 14. Right? I'll be done with this in a second, and then I can put this in the standing. You can write your notes.
Okay.
Okay. So I am going to add, and I'm hoping this burette works because the last one didn't. pH meter in here, it's saying 1. Right, everybody? Let's just say I've got 10 moles of that in there, just to make a nice even number. 987654321 moles. Okay? I am going to add a little bit of NaOH. Can you tell me why it's not pink yet?
Because
Good. I added a little bit of NaOH, just a little bit. I reacted that little bit of HCl, but I still have all of this HCl in there. What pH is that HCl that I have in there?
1.
1. So what's my pH meter going to say? 1. So at the very beginning, my pH said 1. After a splashful, my pH says 1. Let's add a little bit more. How much now? Oh, it stopped again. Okay. How much now? I've added a little bit more. This bit's reacted, but I still have this in excess, so it's still a pH of 1. When will it stop being a pH of 1?
When it's reached the equivalency point.
When all my HCl is gone. Okay? Now at some point I've added 9.999 moles of base. Okay? What color will it be? Colorless. 9.9999 moles of base. I still have a teeny tiny little bit of HCl that's excess, that's still a pH of 1. Did you get that? I'm going to add 1 drop. Let's see if I can get it to happen. Come on, you guys. Maybe not. I'll just let it keep dripping. Eventually, within that 1 drop, I am going to add that 1 drop. It's going to go from excess HCl to completely neutral, 10 moles and 10 moles, and excess 10.1, let's say, NaOH. So, oh, somebody should have said. Whoa. So, at some point here, excess HCl, pH 1, excess HCl, pH 1, keep going, pH 1. At some point, this drop is going to switch very quickly from excess acid to neutral to excess base, because I've added half a drop of extra base. All happening within that 1 drop. pH 1 to pH 14. Okay? And in that time, I'll know I've reached it because the color will change. Ooh. And stay changed. And half a drop. Has to stay for about 10 seconds before you can count it changed. 4, 1,000, 5, 1,000. I think that's one of the most beautiful endpoints I've ever had. How's that for talking and doing at the same time?
Oh?
The braid's gone.
That was 10 seconds though, don't you think?
No.
No?
No.
That's not changing back. Okay. So within that drop, I went from a pH of 1 to neutral and in excess of this base. Okay? All within that 1 drop. Graphically, it looks like this. Okay, I'm going to take that for you. Thank you very much, Donna. Okay, everybody there? It's too close. Low battery. Oh, you need to survive for a little bit longer. Okay, so graphically it looks like this. Please stay. Don't fall. pH of 1 from the very beginning in my flask. No volume. Alkali, by the way, is a base, okay? An alkali is a soluble base. Right, so pH of 1. This is a British sheet, that's why it says alkali, okay? pH of 1. At 0, added for my burette. So this is the pH meter in that Erlenmeyer flask. Okay, I add a bit of base. Oh, still pH 1. Why? Because some of it reacted, but I still have a whole lot of excess HCl. A little bit more, pH 1, pH 1, pH 1, pH 1, until this 1 drop right there. That's 1 drop right there. And in that 1 drop, I went from excess of my acid up to excess base. So pH 14. See that? So up here I have excess base. So to get a color. Blue's better. Here I have excess acid. And this point where color change occurs, what was that called in Chem 20? That's right, an end point. because that's when we end the titration. It can also be called an equivalence point, because that's when the mole ratio is equivalent. Okay, I have exactly, in this example case, 1 mole of HCl for every 1 mole of NaOH, or 10 and 10 in the example I was giving before, exactly in my flask. Everybody get it? So equivalence point or end point at this place. I have excess base here, that's why the pH is 14. I have excess acid here, that's why the pH is 1. This is also called a buffer region, or buffer zone, from here to here. And we'll talk more about the buffer zone when we talk about buffers. But for now, I'll just say that that flat line beforehand is resisting change. Do you see it there, resisting the change? Gobbled up all the base. No, I don't want to change. Gobbled up all the base. No, I don't want to change. So it's called a buffer zone, or buffer region. All right, everybody happy with that? Okay, so if in my burette or my pipette or my conical flask or Erlenmeyer flask, I change something. So this time I'm having a strong acid still in my conical flask, so I still have HCl. Only in my burette, I no longer have NaOH, but now I have a weak alkali. Can you give me an example of a weak alkali, please? Hydrochloric acid, hydrofluoric acid, weak base. Negative, that would be a weak base, because its conjugate acid is a weak acid. Okay, so it looks to me like you guys don't really know how to identify a weak base. There are 2 types of weak bases. One is an insoluble hydroxide. Remember that from yesterday? Aluminum hydroxide was a weak base because it's insoluble. So weak bases, I can't find, in fact I'll just write here, weak base, insoluble hydroxides. Example, aluminum hydroxide. And in your data booklet with your Ka tables, do you remember how we talked about up here are strong acids, like conjugate acid, or pardon me, acids and their conjugate bases, right? Top right-hand corner, strong acids. Bottom, my left and right get mixed up when I'm talking and flipping. So top left-hand corner, strong acids. Bottom right-hand corner, strong bases. Because that's the OH minus. That's the only strong base. The only strong base are soluble OH minuses. All of these then are weak bases. All of them. So you can pick any of these. H2PO4, F minus, NO2 minus. Any of those. Any of them. Okay? Ammonia is another common weak base, NH3. And by base, I mean a proton acceptor, Bronson-Lowry base. Okay, so that's a good example there. Okay, so what have I started with in my flask? I have a strong acid. Do you see that? Strong acid in my flask. I've ended with a weak base. How do I know? Well, the pH is only like 8. So I know it's a weak base. Or if I'm told it's a weak base, I know to end at pH of 8 or 9. This is still the equivalence point. I still have excess base here. I still have excess acid here. This is still the end point or equivalence point. All those terms are still the same. Only remember before you would have said neutralization, acid and base neutralized to salt and water. But yesterday we were talking about how sometimes it's a strong acid in this case, strong acid in a weak base. And so overall I'm still acidic. Remember that? Look, overall in the middle there, still acidic, not neutral. It neutralizes means it brings it closer to neutral, not it becomes 7. So here, my end point hovers around, I don't know, 5, 5.5, 6, but not 7. Does that make sense? Okay. Now if I started with the other way, like in my example here that I have, I've got the base in the burette. What if I put my base in the flask and my acid in the burette? Everybody get that switch? It would be the exact same graph, just backwards. So I'm going to do it on this one. I would have to start here. I would go this way, right? Excess, 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 buffer zone. Endpoint still hovers at 7 because it's a strong and a strong. And then excess of the acid that I'm adding. So this graph can even tell you what's in the flask and what's in the burette. Because I start with, in this case, a base. I start with, in that case, an acid. It tells you what you start with. So it tells you what's in your Erlenmeyer flask. Do you see that? Which is your titrant, which is the thing in the burette, is a titrant. So what's your titrant? What are you adding? I'm adding base, I'm adding base, I'm adding base, I'm adding base. Okay? Any questions so far? Okay, so weak acid and a weak alkali. I'm adding my weak base. You can see, or strong base, pardon me, strong base. You can see I end at 14 because it's a strong base that I finish off with. You can see I start at a weak pH of 5, probably that is. Here's something that's a little new though, this little hiccup. Okay? Whenever you have a weak acid or a weak base in your Erlenmeyer flask, you get this little hiccup. Because it's so weak and you dump a strong thing in there and it goes, at first. And then it can buffer. Okay? So that little hiccup exists if I'm adding something strong to something weak. Other than that, pretty self-explanatory graph. It's just like the others. And then your last one here, right here, is a weak and a weak, and there is no sharp endpoint. There is no beautiful color change within a drop. There's this gross, drawn out, colorless, really light pink, kind of light pink, a little darker pink, right? Like every drop you add, it just gets really, whereas if I were to add another drop to this, it would become overshot instantly, right? Dark pink instantly. So that's a sharp endpoint. It's gone from colorless to a medium pink to a dark pink right away. Whereas this is drawn out. So for these, weak acid, weak alkali, I can't really use an indicator because it's such a drawn out process. I'll never really know when I've reached my endpoint. So for that, I should use a pH meter because the pH meter will tell me 7. Okay, questions on that? Okay. If I am reacting I think I've got a diprotic next. Oh yes. So can you just rub this out? Or have you, I hope you have already, labeled a buffer region, an endpoint, equivalence point, what the titrant is, an area that would have an excess acid, an area that has an excess base. Can you do that? Have you already done it? Right? Okay, tick, 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 tick. Got it. More seconds. All right, ready for the next bit? That was a bit faster than normal, but that's okay. What's polyprotic mean?
It has more than one enzyme to accept or don't.
Right, in this case an acid, so it has more than one proton to donate. Polyprotic. So an example of a polyprotic acid would be H2SO4, because I have 2 protons that I can donate. Right, H2SO4 to HSO4 minus, and I can donate another proton and become SO4 minus. Okay, so each time it donates a proton, it'll go through 1 endpoint, 2 endpoints. So because it's going to go through 2 endpoints, I'm going to get 2 bumps in my titration curve. Okay? Pardon?
How would that be shown by the color? Would it just like...
I would need 2 different indicators. Or actually what they do is they're like, well, which one do you want to look at? And I'm going to use an indicator for that one. Okay? But I would need to think about which indicator to use. So here I have a polybasic compound. So I'm starting in my flask with, what's in my Erlenmeyer flask? The acid or the base? The base is in my Erlenmeyer flask. Is it weak or is it strong? Wrong. Weak, because it's not a pH of 14. Not only that, but the title tells you, do I have a soluble OH minus in there? Soluble OH minus? No. So therefore this is a weak base and this is a strong acid. So I am reacting a weak base to a strong acid. Started with my weak base in as my sample in my Erlenmeyer flask. Okay, and I am titrating the titrant HCl. So the HCl is dripping out of the burette. So here I have Na2CO3, or more importantly, the species CO3 floating about in my flask. Okay, that CO3 is going to accept a proton, right? And it's going to be excess until this equivalence point where all of the CO3 will have gained a proton and been converted into HCO3 So this is the first reaction here. You should be writing on your graph like I am.
I have all that written down.
Then here it's going to accept the second proton and become H2CO3 at point B. So at point A, I've got my CO3 They are grabbing the H3O from the HCl. This is equilibrium because it's a weak acid, strong base. Remember that? So equilibrium arrows, if you ever have a weak acid or base. If it's strong and strong, if they're both strong, it's 100%. 100% arrow. So I've gained 1 proton, and I'm left with the HCl being water, or the H3O being water. So that's happening at point A. Everybody get it? Point B is further down your sheet, which shows the H3O gaining a proton and becoming the H2CO3 and water. Everybody okay? And so the next example would be the polyprotic, where I'm starting with the H3PO4. I'm going to lose 1 proton, become H2PO4-. It's going to lose another proton and become HPO4-2-. And you're asking me, why doesn't it become lose the last proton and become PO4-3-? Remember those solubility? Remember that like waterfall that we can look at for strong acids, strong bases? This last one is so weak, it favors the other side so much, the reactant side. It doesn't really go. But theoretically, I'd have a third bump in there. Theoretically. Okay? And can you see that that ends up being weak base? La 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 la. Everybody okay with that? Okay. Picking indicators. When I am picking an indicator, I want to find an indicator that changes color in this pH range. I don't want it to overlap these humps, those excess points very much. I would really like the whole range to be within my endpoint flat line. Okay? So why do we pick phenolphthalein in Chem 20? So go up here, we'll go to that graph there to remind us what a strong acid and strong alkali graph looks like. And in Chem 20 you indeed use a strong acid like HCl and a strong base like NaOH. You don't use H2SO4 because I don't want two bumps. Okay, so you're going to use something like one proton exchange. And you're going to need something that changes pH in that range. So let's look up phenolphthalein in our data booklets on page 10. And you have a whole pile of indicators and a whole pile of indicator colors here. And you find phenolphthalein and it tells you that it's going to change color between 8.2 and 10. Everybody get that? Does 8.2 and 10 fall on my flat line? You bet. It doesn't encroach on this at all. Okay? So why isn't it a lovely 7? Because I don't need it to be. It's still the same volume. Even if it was 7, it's still the same volume.
Wouldn't you change earlier though? If it was
Not an earlier volume.
no, but like if it was a different indicator, wouldn't it have?
Okay, so we'll talk about a different indicator in a second. Okay. So phenolphthalein changes in these pHs. So when it's down here and the volume is here, what color is it? I mean, you saw colorless, 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 right? Can you figure that out on the table? Why it's colorless to pink means it's colorless before the 8.2. Okay, so down here it's colorless. And above 10, it's pink, according to this table. And here it changes from colorless to pink, so it must be a light pink. Everybody see that? And that's why we choose phenolphthalein. Well, that and it's cheap and cheerful and not very harmful. Let's have a look at choosing a different indicator then. Is there another indicator that I could have picked that falls still in that endpoint vertical zone? How about phenyl red? Let's look at phenyl red. Okay? So phenyl red changes from phenyl red, phenyl red, phenyl red. 6.6 and 8. Is that in my straight up and down zone? Can I choose phenyl red? Nick, will it change color at the same volume? Yeah. You bet.
So it wouldn't change.
So it doesn't matter. It won't change my results. What color would that phenyl red be initially in my conical flask in the acid? Yellow? What color would it be if it was overshot? Red. What color is it going to be in my endpoint? Orange. Because I have a perfectly neutral mixture there. Let's have a look at this mixture. It says that phenyl red is HPR stroke PR minus. Do you see where it says that? What is that talking about? Well, I have a Ka value there. Do you see that? Do you remember what Ka equaled? I'm going to write it up here. Ka equaled H3O plus times A minus divided by HA. Because it's about your acid and water together, right? HA and water. Accepting a proton this way, becoming H3O plus and A minus. Products of reactants. You with me? For every weak acid, this equilibrium exists. For every weak acid, this Ka exists. What is every indicator? A weak acid. They all have Kas. Look at the data booklet, tells us they all have Kas. right? So the Ka for phenolphthalein is 1 times 10 to the power negative 8 equals H3O plus. What's my A minus in this case? What's my HA? HPR, right? What color is HPR? Yellow. What happens when that, oh, by the way, PR for phenol red, PR, right? Phenol red is a huge, you should understand phenol is probably going to have a benzene ring on it. So it's this huge compound. But instead of writing all the carbons and all the hydrogens and all the oxygens, I'm just going to call it PR, just to shorten it up. Okay, so HPR is yellow. I'm going to add the water. It's going to become H3O plus and PR minus, which is red, yellow, acid, alkali. See that? See how these all go together? And so over here I have H3O plus, and my A minus is PR minus, and my HA is HPR. Right? And if I told you that the phenol red that I was using was a 1 mole per liter solution, and I was to ask you to solve for the pH of it, those are always equal. So this is always x squared when I'm talking about Ka, remember from yesterday and for Christmas. So Ka equals x squared over the initial concentration. Oh. And now what looked to be quite a complicated question is actually just a simple Ka question. So don't let it throw you off. It's still a Ka, it's still a weak acid. It just happens to have 2 colors. Why can it go from red to yellow, yellow to red? Why is it orange in the middle? Because it's an equilibrium. Remember Le Chatelier's principle? I can shift this, yellow to red. I can shift it, red to yellow. What happens when I add a base? Well, the base is going to react with this and pull it out and shift it right, which is producing more red. Le Chatelier. See how those all tie together? And if you can see them as the same thing as what we learned before Christmas, all of that is actually pretty easy. Just an application of it. Okay? And I think that's it. That is, yes, that's it. So, down here, I've got some questions for you to do, to practice. And just 2 questions, one, 2 sides there. And that should give you a good understanding of titrations. And then we'll mark it, we'll be done.